Hello, and welcome to Late Night Cosmos, your portal to the mysteries of the universe, where we dive deep into the wonders of space and time. If you're ready to embark on a journey to the farthest reaches of our cosmic understanding, make sure to hit that like button and subscribe to stay up to date with all the mind-bending topics we explore. And before we start, we'd love to hear from you. Where are you watching or listening from? Are you cozy at home, or perhaps stargazing somewhere with a perfect view of the night sky? It's a fitting question, as tonight's adventure is all about the one thing that challenges the very fabric of space itself: black holes. Get comfortable and ready your curiosity, because we're about to unravel the strange and mysterious science of black holes. From their eerie silence to the shocking truths they hold about the nature of our universe, this journey will take us from the heart of a collapsing star to the edge of existence itself. So, let's dive in. Imagine a place so mysterious, so strange, that it seems to defy the very laws of nature. A place where time itself begins to warp, where gravity is so powerful that not even light can escape its grasp. Welcome to the world of black holes, the ultimate frontier of science. These cosmic enigmas challenge everything we think we know about space, time, and the universe itself. From their formation in the catastrophic death of massive stars to their mysterious behavior at the heart of galaxies, black holes have captivated scientists and the general public alike for over a century. They are not just strange, they are paradoxical. In fact, black holes are a reminder that our understanding of the universe is still very much a work in progress. They seem to challenge the limits of our knowledge, forcing us to think in ways that are both unconventional and mind-bending. The journey to understanding black holes begins in the early 20th century, with the work of a brilliant German scientist named Karl Schwarzschild. In the year 1913, Schwarzschild was the first to find a solution to Albert Einstein's equations of general relativity that described a black hole. Before this, the very idea of such a thing was almost science fiction. But Schwarzschild's groundbreaking work showed that if a star were to collapse under its own gravity, it could create a region of space where gravity is so intense that nothing, not even light, could escape. This was the birth of the black hole as a scientific concept. Now, Schwarzschild's discovery was just the beginning, and for many years the idea of black holes was largely theoretical. It wasn't until the 1960s that scientists really began to think about how these cosmic objects could exist in the real universe. One of the major breakthroughs came from physicist John Archibald Wheeler, who popularized the term black hole and further explored their strange properties. But as fascinating as they were, black holes still posed a huge mystery. In the 1970s, two researchers, Jacob Bekenstein and Leonard Susskind, raised a paradox that became known as the information paradox. This was a pivotal moment in the history of black hole theory. According to the laws of quantum mechanics, information about the physical state of matter should never be lost. But black holes seem to break this rule. Anything that fell into a black hole, including all the information about it, appeared to be lost forever, trapped beyond the event horizon, the point of no return. How could this be? It was a dilemma that seemed to defy the fundamental principles of quantum theory. This paradox led to a series of debates and breakthroughs. Bekenstein proposed that black holes might have a kind of entropy, a measure of disorder, that could explain how information could be encoded in the surface area of a black hole. This was a radical shift in thinking. If information could be preserved on the surface of the black hole, it would solve the paradox and reconcile the strange behavior of black holes with the rules of quantum mechanics. But this idea still left many unanswered questions. Then, in the 1990s, another physicist, Juan Maldacena, introduced an idea that would shake the foundations of black hole theory and cosmology as a whole. His proposal, known as the holographic principle, suggested that the entire universe could be understood as a kind of projection. He proposed that all of the information contained in a three-dimensional space could be encoded on a two-dimensional surface at the boundary of that space. This theory, known as ADS/CFT correspondence, offered a new way of thinking about black holes and the nature of reality. Essentially, it hinted that black holes might not be so mysterious after all. They might simply be a natural consequence of the way the universe operates at its deepest, most fundamental level. What's truly mind-boggling is that these groundbreaking ideas were based on the strange and counterintuitive behavior of the smallest particles in the universe: quantum mechanics. It was a collision of two theories: general relativity, which describes the large-scale structure of the universe, and quantum mechanics, which explains the behavior of particles on the smaller scales. For decades, these two theories didn't seem to work together at all, but black holes forced scientists to try to bring them together in a unified theory. As we dive deeper into the world of black holes, it becomes clear just how much we still don't understand. But there's one thing that's certain. Black holes are not just astronomical objects. They are gateways to understanding the very nature of reality. They push the limits of human knowledge, forcing us to question everything we thought we knew about space, time, and the fundamental forces of the universe. And the journey doesn't end here. Every new discovery about black holes opens up even more questions, unraveling deeper layers of mystery and complexity. So, as we venture further into this strange world, we must remember that the black hole is not just a cosmic curiosity. It's a window into the most fundamental laws of nature. And who knows? In unraveling the secrets of black holes, we might just unlock the deepest mysteries of the universe itself. At the heart of black hole theory lies a fundamental question. What is gravity, and how does it shape the universe around us? To understand black holes, we must first grasp the essential concept of gravity and the framework of space-time, the very fabric of the universe in which everything exists. The story begins with one of the most revolutionary ideas in physics, Albert Einstein's theory of general relativity. Einstein's general theory of relativity, published in 1915, transformed our understanding of gravity. Prior to Einstein, gravity was thought to be simply a force that pulls objects toward each other. But what Einstein revealed was far more profound. Instead of seeing gravity as a force in the traditional sense, he proposed that gravity is the result of the curvature of space-time itself. To illustrate this, imagine space-time as a vast, flexible sheet of fabric. When a massive object like a star or planet is placed on this sheet, it causes the fabric to bend and warp. The greater the mass, the deeper the warp. Other objects like planets or moons follow these curves, giving the appearance that gravity is pulling them toward the massive body. But in reality, these objects are simply following the natural curves of the space-time fabric. This idea is most famously illustrated by what we call the rubber sheet analogy. If you place a heavy ball on a stretched-out rubber sheet, the sheet dips around the ball. Smaller objects placed on the sheet will roll toward the ball because of the dip. In the universe, massive objects like the Sun create a similar dip in space-time, which is why Earth orbits the Sun. This is what we call gravity in the context of general relativity. General relativity has been tested and confirmed through numerous experiments. For example, the bending of light around massive objects, what's known as gravitational lensing, has been observed repeatedly. In fact, this phenomenon was first observed during a solar eclipse in 1918, when starlight passing near the Sun was shown to bend, precisely as Einstein's theory predicted. Over a century later, general relativity remains one of the cornerstones of modern physics. But while Einstein's theory beautifully describes how gravity works on large scales, it leaves us with questions about what happens in the extreme environments near black holes. At the heart of a black hole is a singularity, a point where space-time becomes infinitely curved and gravity becomes infinitely strong. This is where general relativity breaks down. So, to understand the true nature of black holes, scientists have explored ways to extend, modify, or even replace Einstein's theory with new ideas that might be able to explain the behavior of gravity at these extreme scales. One alternative theory that has gained attention is called F of R gravity. This theory was proposed by the Italian physicist Salvatore Capozziello and others, and it seeks to generalize general relativity by introducing a function, denoted by F of R, where R represents the Ricci scalar, a mathematical quantity related to the curvature of spacetime. Instead of sticking strictly to Einstein's equations, F of R gravity allows for more flexibility in how spacetime can be curved. The theory suggests that the effects of gravity might be different on cosmological scales, and it has been used to explain phenomena such as dark energy and the accelerating expansion of the universe. This alternative theory could provide new insights into the nature of black holes and their structure, especially at the boundaries where general relativity's predictions begin to fail. Another fascinating area of exploration comes from a field known as non-commutative geometry, developed by the French mathematician Alain Connon. This theory suggests that spacetime itself may not be as smooth and continuous as we think. Instead, at the smallest scales, spacetime could be discrete, made up of tiny, indivisible units. This idea offers a potential bridge between the smooth spacetime of general relativity and the quantum foam that is predicted by quantum mechanics, where space itself might be chaotic and fluctuating. If this theory holds up, it could provide a way to better understand black holes, where the very fabric of spacetime is stretched and bent to extremes. The question of how gravity behaves at these tiny scales leads us to another mind-bending concept: quantum gravity. Quantum mechanics, which governs the behavior of subatomic particles, has long been incompatible with general relativity, which describes the large-scale structure of space-time. One of the biggest challenges in modern physics is finding a theory that can unite these two seemingly incompatible frameworks. One scientist working to bridge this gap is Ariane Finkelstein, who has made significant contributions to the study of quantum gravity. Her work delves into the nature of space-time at the Planck scale, which is the smallest possible scale in the universe, far smaller than even atoms. At this scale, both quantum effects and gravitational effects become significant, and it is here that scientists hope to uncover the true nature of space and time. Finkelstein's research suggests that the smooth fabric of space-time may break down at this tiny scale, leading to a fundamentally new understanding of how gravity behaves in the quantum realm. If space-time behaves differently at the Planck scale, it could dramatically alter our understanding of black holes. For example, quantum gravity might resolve some of the paradoxes associated with black holes, such as the information paradox. Quantum gravity theories suggest that information might not be lost in black holes after all, but rather encoded in subtle ways that we do not yet fully understand. All of these alternative theories, F of R gravity, non-commutative geometry, and quantum gravity, offer new perspectives on gravity and spacetime, particularly in the extreme environments near black holes. They challenge our current understanding and hint that the true nature of the universe is far more complex and mysterious than we ever imagined. As we continue to explore the vastness of space and the enigma of black holes, it becomes clear that gravity is not just a force, but a manifestation of the curvature of spacetime itself. Yet, even with the brilliant work of scientists like Einstein, Capozziello, Connes and Finkelstein, there is still much to uncover. The strange behavior of black holes may one day provide us with the key to understanding the fundamental workings of the universe itself, revealing the hidden nature of reality and the very fabric of existence. In the end, what we know for sure is this: black holes are not just a fascinating feature of the cosmos, they are the very laboratory where the most profound mysteries of physics play out. As our understanding of gravity and spacetime deepens, we come closer to unraveling the ultimate truths of the universe, one black hole at a time. The creation of a black hole is a truly dramatic event in the universe, a cosmic spectacle that begins with the death of a massive star. The life cycle of a star is a delicate balance, with the force of gravity pulling inward while the energy from nuclear fusion pushes outward. But when a star runs out of fuel, this balance tips, and the result can be catastrophic. A stellar collapse that leads to the birth of a black hole. A massive star, much larger than our Sun, spends most of its life fusing hydrogen into helium in its core. This process releases vast amounts of energy, which counteracts the inward pull of gravity. However, when the star runs out of hydrogen fuel, it begins to fuse heavier elements like helium, carbon, and oxygen. As the fusion process moves from lighter to heavier elements, the core of the star contracts and becomes increasingly unstable. The outer layers of the star begin to expand, and it can become a supergiant, a massive, unstable star on the brink of collapse. Now, it's important to understand that this isn't just any collapse. Stars are constantly fighting against gravity, and when the fusion process can no longer generate enough outward pressure to counterbalance the inward pull of gravity, the star's core begins to shrink under its own weight. This triggers a series of events that ultimately results in a dramatic explosion, a supernova. A supernova is one of the most powerful explosions in the universe. It's the star's final, desperate attempt to avoid collapse, but it's also the point at which all the energy and matter that the star has gathered throughout its lifetime are released into space. The outer layers of the star are blasted away, while the core continues to contract, becoming denser and denser. If the remaining mass of the core is enough, it can collapse into a singularity, a point of infinite density, giving rise to a black hole. This process was first explored in depth by John Archibald Wheeler, a physicist who contributed significantly to the understanding of gravitational collapse in the mid-20th century. Wheeler's theory of gravitation collapse explains how the overwhelming gravitational forces of a collapsing star can create the conditions needed to form a black hole. He showed that when the star's core reaches a critical mass, known as the Chandrasekhar limit, named after astrophysicist Subrahmanyan Chandrasekhar, the collapse becomes inevitable, and the core's gravity becomes so intense that nothing, not even light, can escape. This is the birth of a black hole, but the process doesn't end with the collapse of the star. The supernova itself can also play a significant role in the formation of a black hole. As the outer layers of the star explode outward, they create shock waves that can trigger the formation of a black hole if the remaining core is massive enough. In some cases, this process involves what's known as fallback. This idea, explored by physicist M. A. J. Heald, refers to the phenomenon where some of the material from the star's outer layers that was initially expelled during the supernova is pulled back toward the core by gravity. This material falls back onto the collapsing core, adding more mass and potentially causing the formation of a black hole. The fallback mechanism helps explain why some supernovae, rather than leaving behind just a neutron star or a white dwarf, result in the formation of a black hole. It's a crucial piece of the puzzle, showing how a star's final death throes can contribute to the creation of one of the most extreme objects in the universe. But the idea of stellar collapse leading to black holes doesn't always play out in the same way, and some of the more exotic ideas about black hole formation suggest that there may be other, less conventional routes. One such idea involves the concept of cosmic strings, a hypothetical form of matter that could potentially play a role in the creation of black holes. Cosmic strings are theoretical one-dimensional defects in space-time that could have formed in the early universe. They are essentially cracks in the fabric of space-time stretching across vast distances. In some models of black hole formation, proposed by scientists like David Kaus, these cosmic strings could play a role in creating extremely dense regions of space-time that could collapse into black holes. While this is still speculative, it's a fascinating example of how the universe may have more complex and surprising ways of producing black holes than we currently understand. The concept of cosmic strings touches on the deepest, most fundamental questions in cosmology, such as the nature of space-time and the evolution of the universe. The existence of cosmic strings could provide insight into the early universe, just moments after the Big Bang, when the universe was a hot, chaotic soup of particles and forces. Understanding how black holes might form in such extreme conditions could eventually reveal much more about the universe's origins. But for now, the most widely accepted theory of black hole formation remains that of stellar collapse. The stages of a star's life, from its birth in a nebula of gas and dust, to its fusion of lighter elements into heavier ones, to its eventual death in a spectacular supernova, all come together to create one of the universe's most enigmatic objects. The size of the star is crucial in determining whether it will end its life as a black hole or as a less exotic object like a neutron star or white dwarf. For a star to become a black hole, its core must have a mass greater than about 3 times that of the Sun. Once the core reaches this critical mass, the collapse becomes inevitable, and the gravitational forces are so strong that they overwhelm all other forces in nature, leading to the formation of a black hole. In the end, the birth of a black hole is a story of transformation, of a massive star that goes through a cycle of birth, life, and death, and in its final moments becomes something far more strange and far more powerful than it ever was before. It's a reminder of the immense forces at play in the universe, forces that shape the very fabric of space-time itself. The collapse of a massive star into a black hole is both a violent and fascinating process, a process that has captivated scientists for generations. From the contributions of John Wheeler and Hans Bethe to the exploration of fallback mechanisms and the more exotic ideas involving cosmic strings, our understanding of black hole formation continues to evolve. As we look deeper into the hearts of stars and the mysteries of the universe, we uncover more about how these enigmatic objects come to be, and perhaps more about the true nature of the universe itself. One of the most fascinating and unsettling features of a black hole is the event horizon. This is the boundary around the black hole beyond which nothing, not even light, can escape. Once something crosses this threshold, it is gone forever, invisible to the outside world. But what exactly is this point of no return, and how do scientists understand its nature? The event horizon marks the limit of the black hole's influence. It is not a physical surface you can touch, but rather a region of space where gravity becomes so powerful that it overwhelms everything else, including the very fabric of space-time itself. If you were to approach a black hole, you could theoretically travel towards the event horizon without even realizing it, at least until the forces of gravity become so extreme that they begin to tear apart everything in their path. Once crossed, however, escape is impossible. Not even light, the fastest thing in the universe, can travel fast enough to escape the gravitational pull of the black hole. The concept of the event horizon stems from the very definition of a black hole. A black hole is a region in space where gravity is so intense that the escape velocity, the speed needed to break free from the gravitational pull, exceeds the speed of light. This leads to the fundamental idea that once you are within the event horizon, there is no way to get out. To visualize it, imagine an object falling towards a black hole. As it approaches the event horizon, the gravitational forces increase, causing time to appear to slow down for an outside observer. For the object itself, time seems to pass normally, but from a distant perspective it seems to freeze at the event horizon. But the event horizon is not as simple as it might first appear. In fact, scientists have been grappling with alternative theories about the nature of this boundary and how it relates to the larger structure of black holes. For decades, the event horizon was treated as an absolute boundary, a sharp edge that defined the black hole's influence. However, more recent theories have suggested that things may not be so straightforward. One intriguing alternative theory comes from the concept of Lovelock gravity, developed by physicist Gary Horowitz. This theory generalizes Einstein's general relativity to include more complicated geometries and more complex behaviors of gravity. Lovelock gravity allows for the possibility of more intricate event horizons, particularly in higher dimensions. In this framework, event horizons might not be so rigid or well-defined as the classical idea suggests. Instead, they could exhibit more subtle and complex behaviors. Lovelock gravity thus opens the door to exploring black holes in more dimensions than just the familiar three of space and one of time that we experience. It suggests that in certain situations, event horizons could behave in surprising and less predictable ways. In addition to Lovelock gravity, there's another compelling idea proposed by physicists like Stephen Hawking and Malcolm Perry called the soft hair theory. This theory challenges the conventional view of the event horizon as a sharp, impenetrable boundary. Instead, Hawking and Perry suggested that information may not be completely lost once it crosses the event horizon, as was traditionally thought. Their theory introduces the idea of soft hair, a form of information or subtle quantum states that may cling to the event horizon itself. In this view, the event horizon is not a dead end, but instead a place where the black hole retains faint traces of the information that fell into it, encoded in a form that might eventually be accessible. This idea touches on the heart of the long-standing information paradox, which questions whether information that falls into a black hole is lost forever, or if it can be recovered in some way. Soft hair could provide a potential solution to this paradox, suggesting that, while the information may be inaccessible, it is not entirely gone. E.C.G. Sudarshan, an Indian-American physicist, also contributed significantly to the study of black holes, particularly in the context of radiation emitted by black holes. His work on black hole radiation extended the research that led to the discovery of Hawking radiation, which showed that black holes aren't completely black, but actually emit radiation due to quantum effects near the event horizon. Sudarshan proposed that this radiation could be linked to the boundary conditions of the event horizon. In other words, he suggested that the event horizon itself might have properties that influence the kind of radiation emitted by the black hole. This could offer new insights into how black holes interact with their surroundings in the broader universe. Hawking's discovery of black hole radiation was a pivotal moment in physics. It showed that black holes, which were once thought to be perfect cosmic vacuum cleaners, actually emit energy. This discovery led to the realization that black holes are not entirely black, but instead slowly lose mass through this radiation process. The more massive the black hole, the slower the emission of radiation. For extremely massive black holes, this process takes billions of years. But for smaller black holes, the evaporation could be much faster, potentially leading to their eventual disappearance. As intriguing as these theories are, they also complicate our understanding of black holes. The event horizon is no longer just a simple boundary, but a complex interface where fundamental questions about information, quantum mechanics, and gravity intersect. The work of Horowitz, Hawking, Perry, and Sudarshan challenges us to rethink the nature of black holes and the event horizon. Could it be that the event horizon isn't the absolute boundary it once appeared to be? Might it be possible to recover information that falls into a black hole, or is it truly lost forever? Perhaps the most fascinating aspect of these theories is that they push the boundaries of what we know about the universe. They suggest that the event horizon might be a more dynamic and complicated feature than we once thought. Theories like soft hair and Lovelock gravity open up new possibilities for understanding black holes, inviting further exploration into how they might behave, how they might relate to the fundamental forces of nature, and how they might connect to the deepest mysteries of quantum physics. In the end, the event horizon remains a symbol of the unknown, a mysterious threshold that separates the known universe from the dark, uncharted realms of black holes. It is a place where the fabric of space and time breaks down, where the laws of physics as we know them no longer apply in the same way. As scientists continue to explore the nature of the event horizon, we may one day find that its secrets hold the key to unlocking some of the deepest mysteries of the universe, challenging our most fundamental understanding of reality itself. And even though we may never physically cross that boundary ourselves, the quest to understand the event horizon is a journey that brings us closer to understanding the cosmos at its most extreme and mysterious levels. The event horizon is more than just a barrier. It is a gateway to the most profound questions of existence, and it continues to captivate the minds of those who seek to understand the universe in all its complexity. At the very heart of a black hole lies something so strange and so extreme that it challenges the fundamental laws of physics, the singularity. A singularity is a point in space where gravity becomes so intense that space-time itself bends and collapses inward. It's a place where density becomes infinite and the laws of physics as we know them completely break down. Imagine, if you will, a star collapsing under its own weight, its core becoming smaller and smaller until it reaches a point where all its mass is compressed into an infinitely small, infinitely dense space. This is the singularity, the heart of a black hole. It's a region of space-time where the normal rules of physics cease to function in a way we can understand. At this point, gravity dominates everything. The curvature of space-time is so extreme that, according to general relativity, all known laws of physics stop making sense. One of the first to explore the nature of singularities was the brilliant mathematician and physicist Roger Penrose. In the 1960s, Penrose used the powerful tools of general relativity to prove that singularities are not just a theoretical curiosity, but a real feature of black holes. He showed that, under certain conditions, when a massive star collapses to form a black hole, it inevitably forms a singularity at its core. This discovery was crucial, as it suggested that singularities were a fundamental aspect of black holes, not just a mathematical oddity. Penrose's work on singularities led to the Penrose singularity theorem, which states that a singularity must form when a massive star collapses, as long as certain conditions are met. This was a groundbreaking realization that shaped our understanding of black holes. However, this idea raised more questions than it answered. If singularities truly exist, what happens inside them? And perhaps more importantly, what do they mean for the laws of physics? One of the key problems with singularities is that they present a paradox. According to general relativity, a singularity represents a point of infinite density, where gravity is so strong that it overwhelms everything else. But this concept of infinity is something that doesn't sit well with physicists. In the real world, infinity doesn't appear to exist. We don't observe infinite values anywhere in nature, whether in mass, energy, or time. So, what happens to the laws of physics when they encounter such extreme conditions? This paradox is one of the most profound and unresolved questions in modern physics. One potential resolution to the paradox of singularities comes from a concept known as naked singularities. A naked singularity is a hypothetical scenario where a singularity would be visible, unshielded by an event horizon. This would mean that the singularity could be observed from the outside, violating the cosmic censorship conjecture, a principle proposed by Roger Penrose that suggests the singularity should always be hidden behind an event horizon to preserve the smoothness of space-time. The idea of naked singularities has been a subject of much debate, especially as it challenges the foundations of general relativity. Shahar Hod, an Israeli physicist, has worked extensively on the idea of naked singularities. He proposed that under certain conditions these singularities might not be hidden at all, but instead could be exposed, offering a new way to study the extreme physics at the core of black holes. While the concept remains controversial, it opens the door to a deeper understanding of the structure of spacetime and the behavior of matter at its most extreme. But even if naked singularities exist, they would still present a profound problem. If a singularity is visible and accessible, it could lead to unpredictable consequences. Information about the state of matter inside the black hole might be exposed, violating the principles of causality and the preservation of information. This leads us back to the long-standing information paradox, the question of whether information that falls into a black hole is lost forever, or whether it can be recovered in some way. It is here, at the intersection of singularities and information theory, that some of the most mind-bending questions in physics arise. As we explore more exotic black hole solutions, physicists like Carlos Herdero and Alexander B. Balakin have proposed new ideas that challenge the very existence of singularities. Both of these scientists have suggested that black holes may not always have a singularity at their core. Herdero, in particular, has worked on boson stars, a theoretical model where black holes could form from a condensate of bosons, particles that do not obey the Pauli exclusion principle. In these models, the usual singularity is replaced by a more regular finite structure. Balakin has also explored alternative gravity models, suggesting that black holes could exist without the need for singularities at all. These ideas are still highly speculative and not yet widely accepted, but they challenge the standard view that singularities are an inevitable outcome of black hole formation. Instead, they offer a glimpse into a world where the laws of physics might behave in entirely new ways. Could it be that our understanding of black holes needs to be revised, and that singularities might not be a feature of all black holes after all? This is one of the most exciting questions in modern cosmology. To fully resolve the paradoxes and mysteries surrounding singularities, many physicists believe that we need to incorporate quantum mechanics into our understanding of black holes. Quantum mechanics, the theory that governs the behavior of particles at the smallest scales, has proven to be remarkably successful in explaining a wide range of phenomena. However, it doesn't mesh well with general relativity, which describes gravity and large-scale structures like stars and black holes. This is where the need for quantum gravity arises, a theory that seeks to combine the principles of quantum mechanics with the curvature of spacetime described by general relativity. Two leading figures in the quest for quantum gravity are Lee Smolin and Carlo Rovelli. Smolin, a physicist known for his work on loop quantum gravity, has explored how quantum mechanics could be applied to the fabric of spacetime itself, suggesting that spacetime may not be continuous, but rather made up of discrete chunks. This idea has profound implications for the structure of black holes and singularities, as it suggests that at very small scales, the infinite density of a singularity might be resolved by a more granular quantum description of spacetime. Carlo Rovelli, another key figure in quantum gravity, has developed the concept of loop quantum gravity, which suggests that spacetime is quantized at the Planck scale. According to this theory, the singularity at the center of a black hole might not be a point of infinite density, but rather a region where spacetime is fundamentally discrete, preventing the infinite curvature predicted by general relativity. If this is true, it could provide a solution to the singularity problem, offering a new way of thinking about the heart of a black hole. As we consider these theories, we begin to see that the singularity is not just a problem to be solved, but a gateway to deeper insights into the nature of space, time, and the universe. Whether we are dealing with naked singularities, exotic black hole solutions, or the interplay between quantum mechanics and gravity, the singularity remains one of the most intriguing and challenging aspects of black hole theory. The exploration of singularities is more than just a theoretical exercise. It's a journey into the heart of the cosmos, where the limits of our understanding are stretched to their breaking point. The paradoxes surrounding singularities force us to rethink the very fabric of reality, to ask what happens when the known laws of physics fail, and to search for new theories that can bridge the gap between quantum mechanics and general relativity. And in doing so, we may just uncover the deepest secrets of the universe, hidden within the heart of a black hole. When a massive star reaches the end of its life, it embarks on one of the most dramatic and destructive journeys in the universe. The collapse of a stellar remnant into a black hole is a process of immense power and complexity, but it is also one of nature's most intriguing phenomena, the stages leading to the formation of a black hole, begin long before the star's final moments, as the core of the star becomes unstable and the balance between gravity and nuclear fusion finally tips in favor of gravity. In the life of a massive star, gravity and fusion work in harmony to sustain its stability. The core of the star fuses hydrogen into helium, creating an outward pressure that balances the inward pull of gravity. But as the star runs out of fuel, it can no longer sustain this balance. The core collapses, and if the star is massive enough, at least 8 times the mass of our Sun, the collapse leads to the formation of a black hole. The process begins with the star's core contracting under its own weight, leading to a series of explosive events, culminating in a supernova, a violent stellar explosion. The outer layers of the star are blasted away, but the core, now incredibly dense, continues to shrink. If the remaining mass of the core is large enough, it will collapse into a singularity, a point where gravity becomes infinite and space-time itself is infinitely curved. This is the birth of a black hole. Once a black hole is born, it doesn't just sit there, it grows. Black holes have an insatiable appetite for matter, and they can continue to grow by pulling in gas, dust, and even entire stars. But the creation of black holes doesn't end with stellar remnants. Supermassive black holes, which are found at the centres of most galaxies, including our own Milky Way, are a different kind of beast altogether. These giants can be millions or even billions of times more massive than our Sun. How did they form? That question has puzzled scientists for decades. One theory suggests that supermassive black holes could have formed from the quantum fluctuations present in the early universe. Andrew Hamilton, a physicist known for his work on orbits inside black holes, has explored the possibility that the tiny fluctuations in density during the first moments after the Big Bang could have acted as seeds for these supermassive objects. These early fluctuations would have allowed for the rapid accumulation of mass, eventually leading to the formation of a supermassive black hole. This theory suggests that the formation of supermassive black holes could have begun nearly 14 billion years ago, right after the birth of the universe, making them some of the oldest objects we know of in the cosmos. But the formation of supermassive black holes is still not fully understood, and the role of quantum mechanics in their creation is an ongoing area of research. Some scientists believe that black holes could have formed through the mergers of smaller black holes, gradually growing over time. This idea ties in with the ongoing research into the dynamics of black hole mergers, which have become a major focus of modern astrophysics. One of the key breakthroughs in the study of black holes came with the work of Reinhard Genzel and Andrea Ghez. Both of these astronomers were awarded the Nobel Prize in Physics in 2020 for their independent research on supermassive black holes. Genzel and Ghez used advanced observational techniques to study the stars orbiting the centre of the Milky Way. By observing the motion of these stars, they were able to infer the presence of a supermassive black hole, later confirmed to be Sagittarius A, with a mass of around 4 million times that of the Sun. Their work was groundbreaking, as it provided the first direct evidence of a supermassive black hole at the centre of our own galaxy. But their findings have also led to new questions. How did Sagittarius A form? Was it the result of the collapse of a giant star, or did it grow through the accumulation of smaller black holes? These questions are still open for debate, and research into the formation of supermassive black holes continues to evolve. In recent years, astronomers have turned to simulations to help answer these questions. These simulations aim to model the behavior of matter and energy around black holes, simulating how gas clouds, stars, and other objects interact with the black hole's immense gravity. One such simulation, conducted by a team of researchers led by Rainer Spurzheim, has helped shed light on how black holes grow through the accretion of surrounding matter. According to these models, supermassive black holes could have grown rapidly by pulling in vast amounts of gas and dust from their surroundings. Over time, they would have continued to accumulate more mass, eventually becoming the giants we observe today. Another interesting possibility comes from the study of black hole mergers. When two black holes collide, the resulting explosion releases an enormous amount of energy in the form of gravitational waves. These waves, first detected in 2015 by the LIGO collaboration, have provided astronomers with a new way to study black holes. Some scientists believe that supermassive black holes could have formed through a series of mergers between smaller black holes, eventually leading to the creation of the massive objects found at the centres of galaxies today. As we continue to study these enigmatic objects, one thing becomes clear. black holes, both stellar and supermassive, are some of the most powerful forces in the universe. They shape galaxies, influence star formation, and hold the key to understanding some of the deepest mysteries of the cosmos. The formation of black holes, whether from the collapse of a massive star or from the merging of smaller black holes, remains a fundamental question in astrophysics, one that will likely keep scientists busy for many years to come. And while we may not yet fully understand how supermassive black holes come into being, the work of Genzel, Gears, Hamilton, and others has opened the door to new insights. These astronomers and physicists have given us the tools to study black holes in ways that were once unimaginable. And as we continue to observe and model the universe around us, we will likely uncover more about the formation of black holes, how they grow, and what role they play in shaping the cosmos. In the end, black holes are not just the remnants of dying stars, nor are they simply objects to be studied from afar. They are the heart of the universe, the powerful engines that drive the evolution of galaxies, and the mysteries that lie within them. As we continue our exploration of these fascinating objects, we will undoubtedly uncover new layers of understanding about the universe and the forces that shape it. Black holes may be some of the most elusive objects in the cosmos, but they are also among the most important, holding secrets that could one day unlock the deepest mysteries of existence itself. In the early 1970s, Stephen Hawking introduced a groundbreaking theory that forever changed the way we think about black holes. Up until then, black holes were thought to be inescapable, cosmic objects that just accumulated mass and never gave anything back. But Hawking's theory proposed something that seems almost paradoxical. Black holes, according to Hawking, might slowly lose mass and eventually evaporate. This theory, known as Hawking radiation, suggests that black holes are not the eternal cosmic vacuum cleaners that we once thought they were. Instead, they emit radiation and, over incredibly long periods of time, may eventually disappear. The idea of black holes emitting radiation is based on the principles of quantum mechanics, the theory that describes the behavior of particles at the smallest scales. In a vacuum, even in the emptiest regions of space, there are fluctuations in energy. These fluctuations, known as quantum fluctuations, can briefly create pairs of particles, one particle of matter and one of antimatter, that quickly annihilate each other and return to the vacuum. Normally, these fluctuations are short-lived, and the particles disappear almost instantly. But near the event horizon of a black hole, these fluctuations behave differently. Hawking realized that the intense gravity of a black hole could pull these virtual particle pairs apart, with one particle falling into the black hole and the other escaping into space. The particle that escapes carries away energy, and this process causes the black hole to lose a tiny bit of mass. This phenomenon, now known as Hawking radiation, suggests that black holes are not truly black. Instead, they slowly radiate energy and lose mass over time. The more massive the black hole, the slower this process occurs, but over incredibly long periods, billions and billions of years, even the largest black holes could eventually evaporate completely, leaving behind nothing but the radiation they emitted. This idea of black hole evaporation seems to go against our classical understanding of black holes. Traditionally, the event horizon of a black hole was thought to be a one-way barrier, a point of no return where nothing, not even light, could escape. But Hawking's theory suggests that black holes are not entirely black at all. They can emit radiation, and this radiation leads to their gradual shrinking and eventual disappearance. It was a radical shift in thinking, and it opened up new questions about what happens to information that falls into a black hole, an issue that had puzzled scientists for decades. The information paradox is a key part of this story. According to quantum mechanics, information about the state of a system should never be lost. However, if a black hole evaporates completely through Hawking radiation, it seems like the information about anything that fell into it would be lost forever. This idea violates one of the fundamental principles of quantum theory, that information is conserved. How can we reconcile this? How can we understand the fate of the information that falls into a black hole, especially if the black hole eventually disappears? In recent years, a new idea has emerged that complicates our understanding of the event horizon even further. In 2013, physicists Alberto Almeri, Donald Merolf, Joseph Polchinski, and James Sully proposed the firewall paradox. This paradox arose as a potential resolution to the information paradox, and it suggests that an observer falling into a black hole might not experience a smooth, peaceful journey across the event horizon as previously thought. Instead, they might encounter a violent firewall, a region of intense radiation and energy that would instantly destroy anything that tried to cross it. This idea is deeply unsettling because it contradicts the smooth and predictable passage that general relativity predicts for objects falling into a black hole. According to Einstein's theory, as an observer crosses the event horizon, they would not notice anything unusual. Time and space would simply continue as normal. But the firewall paradox suggests that, instead of crossing into nothingness, the observer would be ripped apart by intense radiation the moment they cross the event horizon. This concept has sparked significant debate in the physics community, as it seems to challenge the basic principles of both general relativity and quantum mechanics. If the firewall is real, it could fundamentally alter our understanding of black holes and the nature of spacetime itself. However, the firewall paradox does not provide a conclusive answer. It raises more questions than it answers, particularly about the nature of quantum gravity and the deeper structure of spacetime near the event horizon. Could it be that the smooth crossing of the event horizon is merely an illusion? Or is there a deeper theory of quantum gravity that can reconcile these paradoxes? In response to these paradoxes and the mysteries surrounding black holes, several alternative theories of black hole evaporation have been proposed. One of the most notable comes from Lee Smolin, a physicist known for his work on quantum gravity. Smolin has suggested that the process of black hole evaporation might not be as straightforward as Hawking initially proposed. In particular, Smolin has argued that black holes could be part of a cyclical process, where they do not simply evaporate into nothingness, but rather transform into new, baby universes. According to Smolin's theory, each time a black hole evaporates, it could give birth to a new universe with its own set of physical laws. This concept is part of his broader ideas about cosmological natural selection, which suggests that the evolution of the universe might be driven by the creation of new universes through the collapse of black holes. This theory of black hole evaporation is radically different from Hawking's original proposal. Instead of disappearing completely, black holes could serve as gateways to new realms of existence. In this model, black holes could be the engines of cosmic evolution, spawning new universes with each cycle. While this idea remains speculative, it introduces the possibility that black holes may play a role in the creation of the very fabric of reality itself. Another alternative to Hawking's model comes from the idea that black holes might not actually evaporate at all, but instead may remain stable for an infinite amount of time. Some physicists have suggested that quantum effects near the event horizon might prevent black holes from losing mass through Hawking radiation, effectively halting their evaporation. This idea could have profound implications for our understanding of the long-term fate of the universe. If black holes are truly eternal, they could become the final remnants of the universe, outlasting all other forms of matter and energy. Despite the various alternative theories, one thing remains clear. Black holes are far from simple static objects. They are incredibly dynamic, complex phenomena that continue to challenge our understanding of the universe. Whether through Hawking radiation, the firewall paradox, or the potential birth of new universes, black holes force us to confront some of the most profound questions in physics. What happens to information that falls into a black hole? Can black holes truly evaporate, or do they serve a much larger cosmic purpose? These questions remain unanswered, but they are at the very heart of the mystery of black holes. In the end, black holes are not just cosmic oddities, they are windows into the deepest, most fundamental mysteries of the universe. As we continue to study these enigmatic objects, we move closer to understanding the true nature of space, time, and gravity. Whether through the lens of Hawking radiation, the paradox of the firewall, or the revolutionary ideas of physicists like Lee Smolin, we are constantly rethinking what we know about black holes and the universe itself. Black holes are unlike anything else in the universe. They are invisible, mysterious objects that exist only as shadows in space-time, exerting an immense gravitational pull on the surrounding matter. Yet despite their invisible nature, scientists have developed a variety of clever techniques to study these elusive objects. Observing black holes is one of the greatest challenges in modern astrophysics, but it has led to some of the most exciting discoveries in recent years. The first problem with observing black holes is that by definition, they cannot be seen directly. The event horizon, the point beyond which nothing, not even light, can escape, means that no light or radiation can ever escape from the black hole itself. Without light or other forms of radiation emanating from the black hole, how can scientists detect it? It turns out that although we can't see black holes directly, we can still observe their effects on nearby matter. One of the most powerful tools scientists use to study black holes is the observation of accretion disks. As matter falls into a black hole, it doesn't just disappear, it forms a spinning disk around the black hole. This disk, made of gas, dust, and other material, heats up to incredibly high temperatures as it spirals inward, emitting bright X-rays and other radiation in the process. By studying this radiation, scientists can infer the presence of a black hole and measure its properties such as its mass and spin. But what about the black holes at the centers of galaxies? These supermassive black holes are often surrounded by large amounts of gas and dust, and their effects on surrounding stars and light can be detected. The work of Reinhard Genzel and Andrea Ghez, for which they won the Nobel Prize in Physics in 2020, was pivotal in showing us the first definitive evidence of a supermassive black hole at the center of our own galaxy. They observed the orbits of stars near the center of the Milky Way and concluded that the forces shaping their movement could only be explained by the presence of a massive, invisible object, Sagittarius A, the supermassive black hole that sits at the heart of our galaxy. While detecting black holes through their influence on nearby objects is incredibly useful, the real breakthrough in black hole observation came with the development of the Event Horizon Telescope. This international collaboration, made up of a network of radio telescopes around the world, was designed to observe the shadow of a black hole directly by capturing the light emitted from the surrounding accretion disk. In 2019, the Event Horizon Telescope revealed the first ever image of a black hole, specifically the supermassive black hole at the center of the galaxy M87. The image showed a bright ring of light encircling a dark, nearly perfectly round shadow. This shadow represents the event horizon, the boundary beyond which nothing can escape. The image, though blurry by the standards of conventional telescopes, was a monumental achievement and provided direct visual evidence of black holes. But even more than just capturing an image, the Event Horizon Telescope helped scientists test and confirm many of the predictions made by Einstein's general theory of relativity. The sharpness and clarity of the shadow in the image matched what was expected from general relativity, further solidifying the theory's validity. However, even this groundbreaking achievement is just the beginning of what we can learn from black holes. As our technology improves, we can expect much more detailed observations in the future. One of the key advancements in observational technology comes from the work of physicist Michael Johnson, who has proposed techniques for high-resolution imaging that could allow us to peer even deeper into the heart of black holes. His work focuses on using advanced imaging methods to resolve finer details of the material surrounding black holes, improving our ability to study their structure. With these advanced imaging techniques, scientists hope to learn more about the dynamics of the accretion disk, the behavior of matter near the event horizon, and perhaps even discover new phenomena related to black hole formation and evolution. While direct imaging of black holes and their accretion disks is one way to study these objects, another revolutionary tool has emerged in the form of gravitational wave astronomy. Gravitational waves are ripples in space-time caused by the acceleration of massive objects, such as black hole mergers. These waves travel through the universe at the speed of light, stretching and compressing space as they go. Unlike light or other forms of radiation, gravitational waves can pass through matter without being scattered, allowing us to study even the most hidden and distant black holes. Gravitational waves were first directly detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO. This discovery was a landmark achievement, as it provided the first direct evidence of black hole mergers, when two black holes spiral toward each other and collide, sending out a burst of gravitational waves. Since then, gravitational wave observatories like LIGO and Virgo have detected numerous black hole mergers, giving us a new way to study black holes and their behavior. Nergis Mavalvala, a leading physicist in gravitational wave astronomy, has made significant contributions to this field, working on improving the sensitivity of LIGO's detectors. Gravitational waves offer a unique opportunity to study black holes from a different perspective, one that allows us to detect events occurring far beyond the reach of visible light. With gravitational wave detectors continuing to improve, we can expect to uncover even more about black holes, such as the rate at which they merge, the exact properties of the black holes involved, and perhaps even insights into the earliest moments of the universe. But gravitational wave astronomy is not just about detecting mergers. It also opens up new possibilities for observing the environment around black holes. For example, by studying the way gravitational waves are affected by the space around a black hole, scientists can learn more about the curvature of space-time near the event horizon. This type of observation could provide insights into the behavior of black holes at the quantum level, where general relativity and quantum mechanics must meet. All these different techniques, accretion disk observation, the Event Horizon Telescope, high-resolution imaging, and gravitational wave astronomy, are bringing us closer to understanding these enigmatic objects. They're helping us peel back the layers of mystery surrounding black holes, revealing not just their structure, but also the deeper questions of space, time, and gravity. And the work is far from finished. As observational technology continues to advance, we will no doubt uncover even more about black holes. These discoveries could eventually lead to answers about the nature of space-time itself, and perhaps even open the door to new theories of physics that could fundamentally change our understanding of the universe. For now, black holes remain some of the most mysterious and fascinating objects in the cosmos. Though we can never directly observe the singularity at their heart, the indirect observations we can make are just as valuable, offering us a glimpse into the most extreme environments in the universe. Each new discovery brings us one step closer to understanding the true nature of these cosmic giants and the profound mysteries they hold. The universe is vast, but through our continued observation of black holes, we're beginning to see the incredible ways in which these invisible objects shape the very fabric of space and time. Gravitational waves are ripples in the fabric of space-time itself, created by the acceleration of massive objects, black holes, neutron stars, or even the merger of two of these objects. These waves carry with them information about the most extreme environments in the universe, allowing us to study black holes in ways we never thought possible. The concept of gravitational waves was first predicted by Albert Einstein in his General Theory of Relativity, published in 1915. Einstein's equations suggested that when massive objects move, they should cause distortions in space-time, which would travel outward like ripples on the surface of a pond. However, detecting these ripples directly seemed impossible due to their incredibly faint nature. It wasn't until much later that scientists began to seriously consider how to detect them and what insights they might offer. The first detection of gravitational waves came in September of 2015, a breakthrough that would change the field of astrophysics forever. The team at the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected waves produced by the merger of two black holes, roughly 1.3 billion light-years away. The signal lasted for only a fraction of a second, but it carried with it an enormous amount of information. This detection was the first direct evidence of gravitational waves, confirming Einstein's predictions and opening a new window into the study of black holes. The work of Rainer Weiss, one of the key founders of LIGO, was instrumental in making this achievement possible. Weiss developed the idea of using laser interferometry to measure the minute distortions in space-time caused by gravitational waves. Essentially, LIGO uses two long arms arranged at right angles to each other, forming an L shape. Lasers are fired down each arm, and if a gravitational wave passes through, it causes a tiny distortion in the distance between the mirrors at the ends of the arms. By measuring this distortion, LIGO is able to detect gravitational waves with remarkable precision. The first detection was a momentous event for the scientific community. The collision of the two black holes, each about 30 times the mass of the Sun, produced a burst of gravitational waves so powerful that it could be measured here on Earth. The resulting wave was detected by both LIGO detectors in Hanford, Washington, and Livingston, Louisiana, just 7 milliseconds apart, confirming the event's cosmic origin. This discovery didn't just confirm the existence of gravitational waves, it gave us a direct look at one of the most extreme events in the universe, a black hole merger. But gravitational waves are not just about detecting black hole mergers. They also offer a way to study the interior of black holes, something that is otherwise impossible. Traditionally, black holes are invisible. Nothing can escape from within their event horizons, not even light. But gravitational waves are different. They travel through the universe unaffected by the material that surrounds black holes, so they can reveal the properties of black holes themselves, including information about their mass, spin, and the dynamics of their mergers. This new way of studying black holes has been further advanced by scientists like Miguel Zumalacárregui, who have worked on understanding gravitational wave sources in more detail. Zumalacárregui and others have used simulations to model how gravitational waves interact with black holes and what the waves can tell us about their interiors. This research is crucial because it opens up the possibility of gaining a deeper understanding of the core properties of black holes, information that was previously inaccessible. The insights from gravitational waves help refine our understanding of black hole formation, evolution, and even the mysterious behavior of matter and energy near the event horizon. One of the most significant discoveries in the field of gravitational waves has been the detection of black hole mergers. When two black holes orbit each other, they spiral closer and closer until they eventually collide in an explosive event. These mergers produce intense gravitational waves, and thanks to LIGO and Virgo, another gravitational wave observatory, we've been able to detect several such events. Each merger offers a wealth of information about the black holes involved, their mass, their spin, and the way in which they interact with each other before and during the collision. The first detection of a black hole merger in 2015 was followed by several others, each revealing new aspects of black hole behavior. In 2016, another detection, this time of the merger of two black holes with masses around 14 and 8 times that of the Sun, revealed that black holes can merge more easily than we once thought. Previously, we didn't know if black holes would have enough time to merge before other forces would disrupt them. But these observations suggested that black holes, at least in some cases, can easily find each other and merge, producing gravitational waves detectable here on Earth. These discoveries have profound implications for our understanding of the universe. For instance, they help us probe the fundamental properties of black holes and their role in shaping the structure of galaxies. Some scientists have even speculated that the collisions of black holes could be a primary source of heavy elements in the universe, such as gold or platinum, as these mergers release vast amounts of energy and material into space. The study of gravitational waves from black hole mergers provides an entirely new way of observing the universe, one that complements traditional observations using light and other forms of radiation. But the ability to study black hole mergers using gravitational waves is just the beginning. As our detectors become more sensitive, we'll be able to detect more subtle events, including mergers involving neutron stars, the remnants of exploded stars. These events not only produce gravitational waves, but also release electromagnetic radiation, allowing us to study black holes and their environments in greater detail. The merger of neutron stars, for instance, was detected in 2017, providing a wealth of information about the violent interactions between these dense objects and their role in the formation of heavy elements like gold and platinum. Gravitational waves have also sparked new questions in theoretical physics. One of the biggest challenges is understanding the behavior of black holes at the quantum level. While general relativity explains the behavior of black holes on large scales, quantum mechanics describes the behavior of particles at the smallest scales. The two theories don't always work together in harmony, and black holes are one of the places where the two must come together. Gravitational waves, by offering a way to study black holes directly, provide an invaluable tool for understanding how these two frameworks might ultimately be reconciled. The study of gravitational waves continues to grow, and with each new detection, our understanding of black holes becomes deeper and more nuanced. The incredible advances in technology and the work of physicists like Rainer Weiss, Miguel Zumalacárregui, and the many others involved in gravitational wave astronomy have opened up a whole new era of astrophysics. As the sensitivity of detectors improves, and as more black hole mergers are detected, we're on the verge of uncovering even more profound insights into the nature of black holes, space-time, and the fundamental forces that govern the universe. Gravitational waves have not only confirmed some of the most extreme predictions of Einstein's theory of general relativity, but they've also opened a new chapter in our exploration of the cosmos. The ripples in space-time created by black holes offer us a way to peer deeper into the universe, providing answers to questions that were once thought to be unanswerable. In many ways, gravitational waves are just beginning to reveal their full potential as a tool for exploring the most mysterious objects in the universe. When we think about time, we usually imagine it as a constant, steady flow, each second passing one after the other in the same way no matter where we are. But in the vicinity of a black hole, time behaves in ways that completely challenge our intuitive understanding. Time doesn't just pass the same for everyone. Near a black hole, time itself slows down dramatically, and the deeper you fall toward the event horizon, the point of no return, the more extreme the effects become. This phenomenon is known as time dilation, and it is a direct consequence of the way gravity warps space-time. According to Einstein's theory of general relativity, massive objects like stars and black holes warp the fabric of space-time around them, creating what we experience as gravity. The stronger the gravitational field, the more space-time is distorted. This means that the closer you are to a massive object like a black hole, the slower time moves relative to someone further away from the gravitational influence. Let's imagine two observers. One is standing far away from a black hole, perhaps light years away in deep space, and the other is falling toward the black hole, getting closer to its event horizon. For the observer far away, time would appear to pass normally, but for the one falling into the black hole, time would appear to slow down as they approach the event horizon. From their perspective, everything feels normal. They continue to experience time in the usual way. But from the perspective of the distant observer, the person falling toward the black hole seems to freeze in place, suspended at the event horizon, as if time itself is grinding to a halt. This strange stretching of time occurs because the intense gravity near the black hole warps space-time to an extreme degree. The event horizon, in particular, marks the point beyond which nothing can escape, not even light. As you get closer to this point, space-time becomes more distorted, and the passage of time becomes slower and slower for someone falling in. From an outside observer's point of view, they would never see the person actually cross the event horizon. Instead, they would appear to freeze at the boundary, as time appears to come to a stop. Time dilation is not just a theoretical curiosity. It has real, measurable effects. In fact, it has been confirmed through experiments right here on Earth. For example, scientists have tested time dilation using atomic clocks flown in airplanes and compared them with clocks on the ground. The clocks on the airplanes ticked slightly slower than those on Earth, just as Einstein's theory predicted. This is a result of both the velocity of the planes and the weaker gravitational field at high altitudes. But the effects near a black hole are far more extreme. The consequences of this time dilation can be even more mind-boggling when we consider what happens to objects near a black hole. As you fall closer to the event horizon, not only does time slow down, but your entire body would undergo a process known as spaghettification. This term may sound humorous, but it describes a very real and very violent phenomenon. The gravity near a black hole is so intense that the gravitational pull on the part of your body closest to the black hole is much stronger than the pull on the part farthest away. As a result, your body would be stretched out into an elongated shape, like a piece of spaghetti, because the difference in gravitational forces between your head and your feet would be enormous. This effect, spaghettification, happens because the gravitational gradient near the black hole is so steep. As you get closer, the force on your feet, assuming you're falling feet first, increases dramatically compared to the force on your head. Eventually, these forces would be so powerful that they would tear you apart, stretching you into a thin strand of matter. While this sounds like science fiction, it's a real consequence of the extreme gravity near a black hole's event horizon, and it's one of the reasons why crossing the event horizon is considered an irreversible process. Once something crosses that boundary, it's gone, destroyed by the tidal forces of the black hole. The concept of time dilation and spaghettification near black holes is rooted in the work of some of the most brilliant physicists in history. One such physicist is John Archibald Wheeler, who is often credited with popularizing the term black hole. Wheeler's contributions to our understanding of the nature of black holes helped lay the groundwork for much of what we know today. His work focused on how massive objects like black holes distort space-time and the effects this has on time and gravity. He was also instrumental in developing the idea that the event horizon is not just a boundary, but a key feature in understanding the behavior of black holes. In more recent times, Stephen Hawking's contributions have deepened our understanding of the physics of black holes. His work on black hole thermodynamics and the information paradox has helped explain the relationship between time and space in these extreme environments. While Hawking is perhaps most famous for his theory of Hawking radiation, which proposes that black holes can slowly lose mass over time, his work on the nature of black holes and the space surrounding them has also had a profound impact on our understanding of time dilation and the fate of objects that approach black holes. One of the most striking aspects of the time dilation near a black hole is how it links the idea of time with the very fabric of space-time itself. As gravity bends space-time, it bends time as well. The closer you are to the black hole, the more time is stretched out, and the further you are, the more normal time feels. It's a powerful reminder that time is not an absolute unchanging force. Instead, it's something that can be shaped and warped by the objects around it. Understanding time dilation also forces us to rethink our entire understanding of the universe. We often think of time as something constant, something that ticks away at the same rate no matter where we are. But near a black hole, we learn that time is fluid. It can be warped and bent, and it behaves in ways that we cannot easily predict. This realization opens up a new realm of possibilities in physics, as it shows that the very structure of space-time itself is not fixed. It can be molded, twisted, and altered by the forces of gravity. As we continue to explore the strange and extreme physics near black holes, we are forced to confront these mind-bending ideas. Time dilation and spaghettification are not just abstract concepts. They are real phenomena that occur in the universe's most extreme environments. They challenge our intuitive understanding of time and space, forcing us to rethink what we know about the universe and our place within it. The mystery of black holes is far from over. With each new discovery, we continue to push the boundaries of our understanding, uncovering deeper layers of the universe that challenge the very fabric of reality itself. The study of black holes is not just a study of gravity, it's a study of time itself, and how it is shaped by the most extreme forces in the cosmos. And as we continue to explore the strange physics of black holes, we are reminded that our understanding of time and of the universe is still unfolding in ways that are as mysterious as the black holes we seek to understand. Black hole mergers are among the most violent and energetic events in the universe. When two black holes collide, the resulting release of energy is so immense that it sends ripples through space-time itself, ripples we can detect as gravitational waves. These mergers are not just dramatic cosmic events. They hold the key to unlocking many of the mysteries of black holes, from their formation to their behavior and evolution. At the heart of a black hole merger is a simple yet profound process. Two black holes, each with an immense gravitational pull, slowly spiral toward one another over millions of years, drawn by their own gravity. As they approach each other, their orbits decay, getting closer and closer until they finally collide in an explosion of energy. This collision sends gravitational waves, distortions in space-time, racing outward, carrying away a tremendous amount of energy. These waves travel across the universe, passing through everything in their path, and when they reach Earth, we can detect them with sensitive instruments. The first direct detection of gravitational waves came in 2015, when scientists at the Laser Interferometer Gravitational Wave Observatory, LIGO, detected the waves produced by the merger of two black holes. This was a monumental discovery, confirming the existence of black hole mergers and providing a new way to study these elusive objects. The signal they detected came from the collision of two black holes, each about 30 times the mass of our Sun. The resulting gravitational waves were measured with remarkable precision, marking the beginning of a new era in astrophysics. This breakthrough was the culmination of decades of work, and it opened up a new window into the study of black holes. Gravitational waves allow us to directly observe the behavior of black holes, something that was previously impossible. Unlike light, which cannot escape from a black hole, gravitational waves travel through space unaffected by the material that surrounds the black hole. This means that we can study the inner dynamics of black holes and their mergers without having to rely on the light they emit or absorb. The study of black hole mergers has revealed some surprising and important insights into the nature of these objects. For instance, it has shown that black holes can merge more easily than previously thought. Before these detections, scientists weren't sure if black holes could even find each other and merge, or if their paths would be disrupted by other forces. But the observations of black hole mergers have confirmed that when black holes are close enough, they can indeed merge, sending out powerful gravitational waves in the process. These discoveries challenge our previous assumptions about the dynamics of black holes and give us new tools to study them. As we study black hole mergers, we also gain insight into the role these objects play in the evolution of galaxies. At the centers of most galaxies, including our own Milky Way, there lies a supermassive black hole. These black holes are millions or even billions of times more massive than our Sun, and they influence the dynamics of their host galaxies. Over the course of a galaxy's lifetime, these supermassive black holes may merge with other black holes, leading to the growth of even larger objects. Understanding these mergers is crucial to understanding how galaxies evolve, as black holes are thought to play a central role in the formation and behavior of galaxies. In recent years, astronomers have observed the orbits of stars near the centers of galaxies, leading to the discovery of supermassive black holes. Two scientists who made significant contributions to this field are Reinhard Genzel and Andrea Ghez, who were awarded the Nobel Prize in Physics in 2020 for their independent work on supermassive black holes. Using high-precision observations, Genzel and Ghez were able to map the orbits of stars near the center of the Milky Way and confirm the presence of a supermassive black hole, Sagittarius A. This discovery provided the first direct evidence of the existence of supermassive black holes, and their work continues to shape our understanding of how these black holes influence the surrounding galaxy. But supermassive black holes aren't the only ones merging. In fact, most of the black hole mergers observed so far have involved stellar mass black holes, which are created when massive stars collapse at the end of their life cycles. These stellar mass black holes are much smaller than their supermassive counterparts, but they still pack a tremendous punch. When two of these stellar mass black holes merge, they release a burst of gravitational waves that we can detect on Earth. These mergers can also provide valuable insights into the properties of black holes, such as their mass, spin, and the way they interact with each other. The discoveries of black hole mergers have only just begun. Each new detection of gravitational waves from a merger provides more information about the properties and behavior of black holes. As our observational tools become more refined, we are able to detect more subtle and distant black hole mergers, opening up even more possibilities for discovery. These observations may one day help us answer some of the most fundamental questions in astrophysics, such as how black holes form, how they evolve, and how they influence the universe on the larger scales. One of the most exciting aspects of black hole mergers is the potential for future observations. As the sensitivity of instruments like LIGO and Virgo improves, we will be able to detect even more black hole mergers, including those involving lighter black holes or those occurring in distant galaxies. These new detections will allow us to test our theories of black hole formation and evolution in more detail, and may even provide us with new insights into the nature of gravity and space-time. We are also entering a new era of observation, with the upcoming launch of the James Webb Space Telescope, which will provide us with unprecedented views of the universe in infrared wavelengths. This new telescope will allow us to observe black hole mergers in greater detail, including the light emitted by the accretion disks around black holes as they spiral toward each other. Together with gravitational wave observations, the James Webb Space Telescope will offer a multifaceted view of black hole mergers, allowing us to study these events from every angle. The study of black hole mergers, especially through the detection of gravitational waves, has completely transformed our understanding of these enigmatic objects. The work of scientists like Rainer Weiss, Reinhard Genzel, Andrea Ghez, and many others has opened up new frontiers in the study of black holes, providing us with direct evidence of their existence and behavior. Each new discovery brings us closer to unraveling the mysteries of black holes and their role in the larger structure of the universe. As we continue to observe and study these cosmic giants, we are bound to uncover even more remarkable insights into the nature of space, time, and the forces that govern the cosmos. When we think about black holes, we usually envision an object so dense and powerful that nothing can escape it, not even light. But the deeper we dive into the strange physics of black holes, the more we encounter paradoxes that challenge our understanding of the universe. These paradoxes arise because black holes lie at the intersection of two fundamental pillars of modern physics: general relativity, which explains gravity on large scales, and quantum mechanics, which governs the tiny subatomic world. These two theories, though incredibly successful in their own realms, don't play nicely together when it comes to black holes. To resolve these issues, scientists are turning to new theories that attempt to bridge the gap between the two. Theories of quantum gravity. One of the most exciting approaches to quantum gravity comes from a theory known as loop quantum gravity, or LQG, developed by physicists like Carlo Rovelli and Lee Smolin. Loop quantum gravity is an attempt to describe gravity in terms of quantum mechanics, but in a way that preserves the smooth fabric of spacetime described by general relativity. It posits that space itself is not continuous, but is made up of discrete units, tiny loops or atoms of space. These loops represent the smallest possible scale of spacetime, far smaller than the Planck length, the smallest length scale we can conceive. In this view, space is granular, like a fabric woven from tiny loops rather than a smooth, uninterrupted continuum. The beauty of loop quantum gravity is that it provides a way to reconcile general relativity with quantum mechanics without needing to invoke new particles or dimensions. This theory suggests that at very small scales, the singularity at the center of a black hole might not be a point of infinite density as we once thought. Instead, the quantum structure of spacetime could prevent the formation of a true singularity. According to loop quantum gravity, when a black hole collapses, it may reach a point where the quantum structure of spacetime itself halts the collapse, preventing the creation of a singularity and potentially replacing it with something more manageable, something we don't yet fully understand, but that could be far less extreme than a traditional singularity. This approach to quantum gravity doesn't just challenge our ideas of black holes, it also helps us tackle some of the most famous paradoxes in physics, particularly the black hole information paradox. The black hole information paradox arises from the fact that anything that falls into a black hole seems to disappear completely, lost to the universe forever. Yet, according to quantum mechanics, information cannot be destroyed. If information is lost inside a black hole, then it would violate one of the core principles of quantum theory. This is a dilemma that has puzzled physicists for decades. In the late 20th century, the Argentine physicist Juan Maldacena introduced a theory that has profoundly impacted our understanding of the black hole information paradox and the nature of space-time. This theory, known as the holographic principle, suggests that all of the information inside a region of space can be encoded on the boundary of that space in a lower dimensional form. In other words, the three-dimensional world we experience may be a projection of information encoded on a two-dimensional surface, much like a hologram. Maldacena's ADS/CFT correspondence, which is a part of the holographic principle, suggests that gravity in a higher dimensional space, such as the space inside a black hole, can be described by a quantum field theory in a lower dimensional space, like the surface of a black hole. This idea proposes that the information inside a black hole is not lost, but instead encoded on its event horizon. This groundbreaking theory has far-reaching implications for our understanding of black holes. According to the holographic principle, the information that falls into a black hole may be preserved in some form, possibly as soft quantum states on the event horizon, rather than being lost forever. The holographic principle has also led to new ways of thinking about the nature of black hole interiors. If the interior of a black hole is effectively described by a lower dimensional quantum theory on the surface of the black hole, then it might be possible to study the quantum behavior of black holes without needing to probe the singularity itself. This concept has given rise to new theories of how spacetime behaves inside black holes, suggesting that the interior might not be as strange and incomprehensible as once believed. These new ideas about black holes and quantum gravity are not just theoretical musings, they have practical implications for the future of black hole research. Physicists like Fotini Markopoulou are exploring how quantum gravity could provide new insights into the structure of spacetime itself. Markopoulou's work on the quantum structure of spacetime suggests that the fundamental nature of space and time is not continuous, but instead exists in discrete units. These quantum units could help explain how black holes form and how they evolve. By studying the quantum behavior of spacetime, researchers hope to unlock a deeper understanding of the black hole interior and the fundamental forces that govern the universe. But while the theories of loop quantum gravity and the holographic principle are exciting and promising, they are still very much works in progress. We are still far from a complete understanding of quantum gravity, and much more research is needed to fully integrate it with our understanding of general relativity. One of the biggest challenges is that we don't yet have the tools to directly test these theories. The smaller scales at which quantum gravity operates are far beyond the reach of current experiments. To truly understand the nature of black holes at the quantum level, we'll need new technologies and new ways of observing the universe. Despite these challenges, the idea that black holes may not contain singularities after all is a fascinating and transformative one. If quantum gravity theories hold true, black holes could be much more complicated and nuanced than we once thought. They may not be the voids of infinite gravity and destruction that we imagine, but rather objects where the very fabric of space-time is stretched and shaped in ways we cannot yet fully understand. The pursuit of quantum gravity and the study of black holes is not just about solving one paradox or one mystery. It's about challenging the very foundations of physics. It's about rethinking our understanding of space, time, and reality itself. As we continue to study quantum black holes, we may find that the black hole information paradox is just the beginning of a much deeper journey into the heart of the cosmos. What is the nature of space and time at the smallest scales? What happens when gravity and quantum mechanics finally meet? These are the questions that drive scientists like Carlo Rovelli, Lee Smolin, Juan Maldacena, and Fotini Markopoulou to push the boundaries of knowledge, striving for answers that could change the way we understand the universe forever. Black holes, once thought to be the most mysterious and impenetrable objects in the universe, may ultimately be the keys to unlocking the deeper secrets of physics itself. Black holes, those mysterious cosmic giants, have captured the imagination of people for generations. They are the ultimate symbol of the unknown in our universe. Vast, invisible, and strangely compelling. These enigmatic objects have become central figures in science fiction, appearing in novels, films, and TV shows, often as portals to another dimension, or as the final frontier where the laws of physics break down. But these portrayals, while often fantastical, are more grounded in real science than you might think. Over the years, science fiction has shaped the public's understanding of black holes, and in turn, filmmakers and writers have worked with scientists to ensure that their depictions are rooted in scientific theory, offering an intriguing blend of imagination and reality. One of the most iconic and scientifically accurate depictions of black holes in modern cinema came in the film Interstellar, directed by Christopher Nolan and released in 2014. The movie follows a team of astronauts who venture through a wormhole near Saturn to find a new home for humanity. Along the way, they encounter a supermassive black hole called Gargantua, which plays a pivotal role in both the plot and the film's visual spectacle. To bring Gargantua to life on the screen, Nolan enlisted the help of renowned physicist Kip Thorne, a Nobel laureate and one of the world's leading experts on general relativity and black holes. Thorne worked closely with the filmmakers to ensure that the portrayal of the black hole, its accretion disk, and the effects of gravitational time dilation were as scientifically accurate as possible. Thorne's input was crucial, as Interstellar sought to depict the behaviour of a black hole in a way that had never been seen before in a movie. The result was breathtaking. The image of Gargantua, its swirling accretion disk glowing brightly, became one of the film's most visually stunning sequences. But it wasn't just about aesthetics. The movie also introduced viewers to the concept of gravitational time dilation, a real effect predicted by Einstein's theory of general relativity. According to this theory, the stronger the gravitational field, the more time slows down. Near a black hole, this effect becomes extreme. In Interstellar, as the astronauts approach Gargantua, they experience time passing much more slowly than back on Earth. In one dramatic moment, they visit a planet near the black hole, where 1 hour on the surface equals 7 years outside its gravitational influence. This concept, while dramatic, is rooted in real science. The collaboration between Thorne and the filmmakers extended beyond just time dilation. Thorne also helped ensure that the depiction of the black hole's accretion disk, the glowing ring of hot gas and dust that surrounds the event horizon, was based on the most up-to-date scientific models. In fact, the visual effects team used Thorne's equations to accurately simulate the way light behaves in the intense gravitational field of a black hole, creating a look that was not only visually stunning but scientifically accurate. The film even contributed to real scientific research, with some of the simulations developed for the movie being used by scientists to study black holes and how they bend light. Beyond Interstellar, black holes have appeared in countless other science fiction works, often serving as symbols of ultimate mystery or gateways to other realms. In Arthur C. Clarke's 2001, A Space Odyssey, the character Dave Bowman travels through a mysterious monolith near Jupiter and experiences a journey that leads him through a black hole, opening up a realm of unknown possibilities. While the film took some liberties with the science of black holes, it sparked the imagination of many viewers and prompted discussions about the true nature of these objects. In literature, black holes have similarly fascinated authors, providing a rich backdrop for exploring themes of time, space, and the unknown. In his novel, The Black Hole, Peter C.B. Phillips imagines a scenario where a spaceship is sent to explore a supermassive black hole, its crew encountering the challenges of navigating extreme gravity and time dilation. Many of these stories take the concept of black holes into the realm of speculation, imagining them as portals to other dimensions or the means of travel through time. These portrayals in popular culture are not just for entertainment, they also shape the way we think about black holes and inspire real scientific inquiry. The public's fascination with black holes has led to greater interest in the actual science behind them. As a result, many scientific researchers have turned to these fictional depictions to explain real phenomena and make complex concepts more accessible to the general public. One way these fictional representations contribute to our understanding is by encouraging people to ask questions about the nature of black holes. What happens inside them? How do they form? Can they be used for time travel? These questions, although often inspired by science fiction, lead to deeper discussions about the true nature of the universe, prompting real scientific investigations. While the science behind black holes can be difficult to grasp, these movies and books provide a stepping stone for curiosity. They offer an entry point to understanding concepts like spaghettification, the process by which objects are stretched and torn apart as they approach a black hole's event horizon. In many science fiction stories, characters experience this effect when they venture too close to a black hole, and while these depictions are often exaggerated, they are based on the real science of tidal forces and gravitational gradients. The concept of spaghettification is rooted in the laws of general relativity, which describe how the immense gravitational pull near a black hole can stretch objects into long, thin shapes as they approach the event horizon. These fictional representations also spark discussions about wormholes, hypothetical shortcuts through space-time that are often associated with black holes in popular culture. In films like Interstellar and Contact, wormholes are used as a means of travel between distant parts of the universe, offering a way to bypass the vast distances of space. While wormholes remain speculative and have not been observed, they are consistent with some solutions to Einstein's equations, and they remain a subject of scientific study. The collaboration between scientists and filmmakers to portray black holes accurately, particularly in Interstellar, demonstrates the growing intersection of science and popular culture. It's a reminder that science fiction is not just about creating imaginative worlds, but can also serve as a bridge between the public and the scientific community. By bringing complex scientific concepts to life, these portrayals help spark curiosity and inspire the next generation of scientists, engineers, and thinkers to explore the real mysteries of the cosmos. In the end, black holes in popular culture are more than just plot devices. They are symbols of the unknown, embodying our quest to understand the universe and the fundamental forces that govern it. While science fiction takes some liberties with the science, it's clear that these fantastical stories are built upon the real principles of physics, and they continue to inspire real-world research into the nature of black holes and the very fabric of space-time itself. As our understanding of black holes deepens, the line between science fiction and science fact becomes ever more blurred, and the mysteries of the universe continue to captivate both the imagination and the intellect. Supermassive black holes are more than just exotic objects that lurk at the centers of galaxies. They play an essential role in shaping the formation and evolution of those galaxies. These cosmic giants, millions or even billions of times more massive than our Sun, influence the growth and structure of the galaxies they reside in, affecting everything from star formation to the overall dynamics of galactic systems. One of the most significant ways supermassive black holes shape galaxies is through their influence on star formation. In the early universe, galaxies were often bustling with activity, with stars forming rapidly in dense clouds of gas and dust. But as galaxies grew, so did their central supermassive black holes. The growing gravitational influence of these black holes can regulate the rate at which stars form by heating the surrounding gas, or even expelling it altogether. This process is known as feedback, and it plays a critical role in the balance of energy within a galaxy. For instance, when material falls into a supermassive black hole, it forms an accretion disk, a swirling hot mass of gas and dust that emits enormous amounts of energy. This energy can be so intense that it drives powerful winds and outflows, pushing gas away from the center of the galaxy. Without this gas, star formation is slowed or even halted, and the galaxy's growth is regulated. In some cases, this feedback process can even lead to the quenching of star formation, turning a once active galaxy into a red and dead system where stars no longer form. The work of Reinhard Genzel and Andrea Ghez has been pivotal in our understanding of how supermassive black holes affect their host galaxies. In 2020, both Genzel and Ghez were awarded the Nobel Prize in Physics for their groundbreaking research on the supermassive black hole at the center of our galaxy, Sagittarius A. Over decades of careful observation, they tracked the orbits of stars around the center of the Milky Way, providing the first definitive evidence of the existence of a supermassive black hole. Their research has helped confirm that these central black holes are not just passive objects, but active players in the dynamics of galaxies. By measuring the motion of stars near the center of the Milky Way, Genzel and Ghez were able to determine the mass of Sagittarius A, which is about 4 million times the mass of the Sun. Their findings also demonstrated how the black hole's gravity affects the surrounding region, influencing the motion of stars and shaping the galactic environment. But the role of supermassive black holes in galaxies isn't just about regulating star formation. They also drive some of the most energetic phenomena in the universe, such as active galactic nuclei, AGN, and quasars. These are among the brightest objects we observe, often outshining their entire host galaxies. An active galactic nucleus is a region at the center of a galaxy where a supermassive black hole is actively accreting matter. As material falls toward the black hole, it forms an accretion disk which gets heated to extreme temperatures, emitting vast amounts of energy across the electromagnetic spectrum, from X-rays to radio waves. Quasars, which are a type of AGN, represent some of the most energetic and distant objects in the universe. The energy output of a quasar can be billions of times greater than that of the Sun. This intense radiation comes from the matter swirling around the black hole as it accelerates and heats up. In some cases, the energy emitted by quasars is so powerful that it can affect the entire galaxy, pushing gas away and halting star formation, much like the feedback mechanisms that slow down growth in some galaxies. This is just one example of how supermassive black holes can act as both engines of creation and destruction in the universe. While AGN and quasars provide a glimpse into the active life of supermassive black holes, they also offer valuable insights into the early universe. Many quasars are observed at extreme distances, meaning they are seen as they appeared when the universe was very young, just a few billion years after the Big Bang. By studying these distant quasars, astronomers can learn more about the conditions that existed during the formation of galaxies and the role that supermassive black holes played in shaping the cosmos during its earlier stages. The relationship between supermassive black holes and galaxies is deeply intertwined. As galaxies evolve, so do the black holes at their centers. In some cases, the growth of a supermassive black hole is closely tied to the formation and growth of the galaxy itself. The feedback from the black hole, through energy released by the accretion disk, outflows, and the eventual formation of AGN, can regulate the growth of stars, influence the structure of the galaxy, and determine how the galaxy evolves over time. In other cases, the black hole's influence can help shape the size and shape of the galaxy, particularly in elliptical galaxies where star formation has long since ceased. One of the most compelling aspects of studying the role of supermassive black holes in galaxy evolution is that they provide clues about the processes that shape the universe as a whole. Supermassive black holes are thought to have formed early in the universe's history, potentially just a few 100 million years after the Big Bang. Understanding how they form, grow, and interact with their host galaxies could help us understand the larger processes that govern the formation of the first galaxies, stars, and structures in the early universe. But despite the groundbreaking discoveries made by scientists like Genzel and Ghez, many questions remain about the precise role that supermassive black holes play in galaxy evolution. How do they form so quickly after the Big Bang? How do they grow to such enormous sizes? And what drives the incredible energy output seen in AGN and quasars? These are questions that continue to challenge astronomers and physicists alike. New observational techniques, such as the use of gravitational wave detectors like LIGO and Virgo, may eventually provide more insights into the role of supermassive black holes in galaxy formation. Gravitational waves, which are ripples in spacetime caused by the motion of massive objects like black holes, offer a way to study the most extreme events in the universe, including the mergers of supermassive black holes. By detecting these waves, scientists can learn more about how these black holes interact with each other and how their mergers affect the surrounding galaxies. As our ability to observe the universe improves, particularly with advancements in telescope technology like the James Webb Space Telescope, we are likely to gain more detailed information about the role of supermassive black holes in the formation and evolution of galaxies. With each new discovery, we move closer to understanding how these cosmic giants influence the very structure of the universe. The relationship between black holes and galaxies is one of the most profound and fascinating topics in modern astrophysics. Supermassive black holes are not just the enigmatic centers of galaxies, they are active, powerful forces that help shape the galaxies they inhabit. From regulating star formation to powering quasars and driving the evolution of galaxies over billions of years, these black holes are among the most important and dynamic objects in the universe. As we continue to study them, we are sure to uncover more about the intricate dance between these cosmic giants and the galaxies they help create. As we look toward the future of black hole research, we stand on the cusp of what promises to be an exciting era in astrophysics. The mysteries of black holes have captivated scientists and the public for decades, and thanks to advances in technology and observational techniques, we are now in a position to answer some of the biggest questions about these enigmatic objects. The next few years could bring some groundbreaking discoveries that not only reshape our understanding of black holes, but also have profound implications for our understanding of the universe itself. One of the most anticipated tools for future black hole research is the James Webb Space Telescope, set to launch in the coming years. Unlike its predecessor, the Hubble Space Telescope, which primarily observes the universe in visible and ultraviolet light, the James Webb Space Telescope is designed to observe in the infrared spectrum. This will allow it to peer into regions of space that are otherwise obscured by dust and gas, providing clearer views of distant objects, including black holes. One of the telescope's key goals is to observe the environments around supermassive black holes at the centers of galaxies. The infrared capabilities of Webb will enable scientists to study the accretion disks of these black holes in unprecedented detail, observing the material that spirals inward and emits radiation before crossing the event horizon. Webb will also be able to look deeper into the early universe, examining the first galaxies and the formation of the supermassive black holes that likely played a role in shaping them. With its ability to observe galaxies billions of light-years away, Webb promises to offer a glimpse into the formation and evolution of black holes and galaxies in the distant past. These observations could provide valuable insights into how supermassive black holes grew so quickly in the early universe, a puzzle that has perplexed scientists for years. In addition to the James Webb Space Telescope, another exciting area of future research is the detection and study of gravitational waves. Gravitational waves, ripples in space-time caused by the acceleration of massive objects, have already provided a wealth of information about black hole mergers. Since the first detection of gravitational waves by LIGO in 2015, astronomers have used these waves to observe black hole collisions and measure the masses, spins, and other properties of the black holes involved. But this is just the beginning. The next generation of gravitational wave observatories is expected to greatly enhance our ability to detect and study black hole mergers. One such observatory, the Einstein Telescope, is planned to be much more sensitive than current detectors like LIGO and Virgo. It will be able to detect even weaker signals from more distant black hole mergers, providing a more detailed and complete picture of how black holes form and evolve over time. The LISA, Laser Interferometer Space Antenna mission, which is set to launch in the coming decade, will also be a game-changer. LISA will be a space-based observatory designed to detect low-frequency gravitational waves, which are produced by larger and more distant black hole mergers. This will allow us to study black hole mergers in a new way, gaining insights into the earliest moments of the universe and the formation of supermassive black holes. As these advanced gravitational wave detectors come online, we can expect to learn much more about the dynamics of black holes. For example, by studying the gravitational waves produced by mergers, we can gain insight into the internal structure of black holes, such as their spin rates, masses, and how these properties change during mergers. This could help resolve some of the long-standing questions in black hole physics, such as how black holes grow, how their spins align, and how they interact with their surrounding environments. These discoveries may also shed light on the process by which supermassive black holes form and grow over time. In parallel to these observational advances, there is also ongoing progress in theoretical frameworks that seek to reconcile general relativity and quantum mechanics. One of the leading approaches is the theory of quantum gravity, which aims to describe the behavior of space-time at the smallest scales, where quantum effects cannot be ignored. While general relativity works incredibly well on large scales, such as the size of galaxies and black holes, it doesn't account for the quantum behavior of matter and energy. To truly understand black holes, we need a theory that can describe both the vast curvature of space-time near a black hole and the quantum effects that dominate at the smallest scales. Two of the most prominent figures in the field of quantum gravity are Carlo Rovelli and Lee Smolin. Their work on loop quantum gravity has provided a promising framework for understanding the quantum nature of space-time. Loop quantum gravity suggests that space-time is not a smooth continuum, but instead is made up of discrete units, or atoms of space. This view could help resolve some of the paradoxes associated with black holes, such as the nature of the singularity at the center. In this framework, the singularity may not be a point of infinite density, but instead, the quantum nature of space-time may prevent the formation of such a singularity, offering a new way to understand the interior of black holes. Another important development comes from the holographic principle, which was introduced by physicist Juan Maldacena. The holographic principle suggests that the information contained in a three-dimensional region of space can be encoded on a two-dimensional boundary. This has profound implications for our understanding of black holes, as it suggests that the information contained inside a black hole may not be lost, but instead encoded on its event horizon. This could potentially resolve the black hole information paradox, which questions whether information that falls into a black hole is lost forever, or whether it can be recovered in some way. The holographic principle has opened up new ways of thinking about black holes, providing a potential solution to one of the most vexing problems in theoretical physics. As we look ahead, these theoretical frameworks, combined with the new observational technologies we have at our disposal, offer the potential to answer some of the biggest questions in black hole research. The intersection of quantum mechanics and general relativity remains one of the greatest challenges in physics, and black holes are at the heart of this puzzle. Through the study of gravitational waves, the insights from the James Webb Space Telescope, and the development of new theoretical models, we may finally begin to understand the true nature of black holes, their role in the universe, and the very structure of space-time itself. Ultimately, the future of black hole research is a journey into the unknown. Every new discovery brings us closer to unlocking the secrets of the cosmos, from the fundamental nature of space and time to the formation of galaxies and the evolution of the universe. As we continue to explore the most extreme objects in the universe, we will undoubtedly find that the mysteries of black holes are not just puzzles to be solved. They are windows into the deepest questions of existence, awaiting discovery by the curious minds that dare to seek answers. As we reflect on the strange science of black holes, we find ourselves standing at the edge of one of the most profound mysteries in the universe. Throughout this journey, we've ventured through the dense, dark regions where time and space twist and bend in ways that challenge the very fabric of reality. From the paradoxes of their formation and behavior to their influence on galaxies and stars, black holes offer a unique lens through which we can explore the cosmos, pushing the boundaries of what we know about the universe. At their core, black holes are not just astronomical objects. They are windows into the deepest questions of physics. They represent the intersection of two powerful yet conflicting theories, general relativity and quantum mechanics, and the ongoing quest to reconcile them continues to drive much of the research in modern physics. Whether it's understanding the strange effects of time dilation near their event horizons, the nature of the singularities at their centers, or the mysterious role they play in galaxy formation, black holes are an ever-present reminder that there is so much we have yet to discover. The investigations into black holes are not just academic. They are expanding the very boundaries of science. As scientists like Reinhard Genzel, Andrea Ghez, Kip Thorne, and others continue to explore the mysteries of black holes through groundbreaking work in both theory and observation, we are uncovering new layers of understanding. Tools like the Event Horizon Telescope and the James Webb Space Telescope, along with gravitational wave observatories like LIGO, offer us unprecedented insights into the behavior of black holes, and the discoveries we've made so far are just the beginning. Perhaps the most exciting aspect of black hole research is the sense of awe it invokes. We are not just solving puzzles, we are venturing into the unknown, exploring realms of space and time that stretch our imaginations and force us to rethink the very nature of the universe. Black holes, with their immense gravitational pull and their ability to distort space and time, are like cosmic laboratories where the laws of physics are tested to their extremes. They remind us that the universe is far more complex and mysterious than we can fully grasp, and they inspire a sense of wonder that has been a driving force behind scientific inquiry for centuries. Even as we inch closer to understanding the mysteries of black holes, we know that there is still much we don't know. Questions about the nature of quantum gravity, the information paradox, and the true structure of space-time remain unresolved. These unanswered questions only add to the allure of black holes, urging us to continue exploring and to push the boundaries of what we think is possible. The future of black hole research holds the promise of even more groundbreaking discoveries, and with each new finding, we come closer to unlocking the ultimate secrets of the cosmos. As we continue to delve deeper into these cosmic enigmas, we are reminded of how much more there is to learn about the universe. Black holes challenge our understanding of time, space, and reality itself, but they also spark our curiosity, driving us to explore and discover the uncharted mysteries that lie beyond our reach. The journey to understand black holes is far from over, and as we continue to explore, we are bound to encounter even more awe-inspiring and mind-bending discoveries. The mysteries of the universe are vast and complex, and black holes, in all their strange glory, will undoubtedly continue to be at the forefront of our quest for knowledge.